Yeah, yesterday we saw how to deal with the nonlinear functions. We said a function is said to be nonlinear if the power on the variable in which it is defined is neither 0 nor a 1. That is when it can be either a negative or it can be beyond 1. For instance, you can have x squared, x cubed, and so on. Now, today we want to apply the knowledge we studied yesterday, where we said if you meet a nonlinear function in these PDFs of random variables, you get the intercepts, you get the values at endpoints, and the turning points plus their nature. So we spotted some functions that were nonlinear. We found the intercepts and the turning points plus their nature. So we want to improve that knowledge in the continuous random variables. So before us, the example that we are going to start with says the random variable x has a PDF given by this, where f of x is equal to x squared. That is when x is bounded between 0 and 4. 0 elsewhere, where k is a constant. In Roman 1, they want us to get the value of k. In Roman 2, they want that probability. And in part B, they want us to sketch this nonlinear PDF, which is f of x is equal to kx squared. Now we said that if you want to find the value of any unknown for continuous random variables, there is a property of the PDF that says, so in part A, as part of the solution, in part A Roman 1, we agree that if you want any unknown, when you integrate, you want the value of k. So if you integrate from negative infinity to positive infinity, and you integrate in the PDF with respect to x, the answer should be 1, which implies if we integrate, our f of x is kx squared, our f of x is kx squared. That is when x runs from 0 to 4. So here there is negative infinity, we are going to put this. Where there is positive infinity, we are putting the upper limit. So we shall have a 0 to 4. Where there is f of x, we are putting this. So this is the kx squared dx is equal to 1. So that k is a constant, and therefore we pull it outside the integral. So we shall have a k integral from 0 to 4 of x squared dx. The answer should be a 1. So we shall have our k, the integral from 0 to 4 of x squared dx. The answer is the 1. So this is a constant. If I square it here aside, what you get when you integrate x squared? Say you increase the power by 1 and you divide by the new power. So we are going to have x plus 1, x power 2 plus 1, which is x cubed over 3. We have integrated from 0 to 4, and the answer should be 1. So we shall have our k into, put in the upper limit, we are going to have 4 cubed over 3. Put in the lower limit, you can put these lines to indicate that we are done with substituting in the upper limit, and we now want to substitute in the lower limit. Put in the lower limit, we are going to have 0 cubed over 3, and all that should be a 1. So even when this one presses a 0, we don't write the 0 before substituting in. So this step is very important. Now after that, we are going to have our k into 4 cubed, that is a 64 over also not be used to find any unknown probability because it is a curve. So you can't generate any shape, and then otherwise when you generate any shape, you have some errors. So a graph of a nonlinear PDF can only be sketched to show how it's shape, but you can't use it to really find any unknown constant and also find any unknown probabilities. You only use the graphs of linear PDFs to do so, to find the value of the unknown and also to find the value of the unknown probabilities. Now for this case, where the graph is nonlinear, we don't use it to solve anything. So in the part B, we wanted the sketch of f of x. So the first step is to identify f of x in the different intervals. So my f of x is 3 over 6 f of x squared. This is when x lies between 0 and 4. The next step is to generate the values at any points. But before generating them, you ask yourself, is this thing linear or non-linear? Now our function f of x, which is 3 over 6 for x squared, it is a non-linear PDF. So we are going to find the values at any points, but we shall also find the turning points because the function is non-linear. So straight away we are heading to the values at any points. Now for our values at any points, we say to read off the function. Our function is f of x is equal to this. The end points have an x coordinate of 0 and 4. So initially, the first initial point, that is when x is the starting value, which is 0. So when x is 0, f of 0 is going to be 3 over 6 therefore into 0 squared, and our f of 0 is going to be 0, which means our curve must start at 0, 0. We also need the other end point, and that is when x is the extreme value. So when x is a 4, our f of 4 is going to be 3 over 6 therefore into 4 squared, and our f of 4 is going to be a 3 over 4. So our f of 4 is that, and it implies all our points must be written in the form x, f of x. So it means we begin with the x coordinate followed by the f of x coordinate. We begin with the x coordinate followed by the f of x coordinate. That is why in this we started with x as 0, then f of x was also 0. Then in this one, our x is a 4. Then our f of x is a 3 over 4. Those are the values at the end points. Now, because this thing is non-linear, we can also find the intercepts. Then we interpret them. Though in most cases the intercepts may not cause any significant change. So let us also go to the intercepts. Or before the intercepts, let us begin with the turning points. Some people may forget these relevant ones. So we are now heading to the turning points. We say if you want to get the turning points, you must have the first derivative and equate your first derivative to what? To a 0. So our function is f of x is have the x-coordinate of the turning point. So my first derivative of x is a 3 over 60, not a 3 over 64. It is a 6 over 64x. So it is 6 over 64x, but we are equating this to 0. So f prime of x at the turning point is a 0, which means the 6 over 64x is 0, and our x will definitely be a 0. After getting the x-coordinate of the turning point, we also agreed that you get that x-coordinate of the turning point and you substitute it in the original function. After substituting it in the original function, you get your y coordinate. There would be y coordinate of the turning point. Now our turning point must be in the form x f of x, but we have this already. We need this. So our f of x is a 3 over 6 we say you inspect f double prime at the x coordinate of the turning point. So we are going to get this 0 and substitute it here. Our f double prime of 0, because this is the constant function, is going to remain as 6/6, therefore. Now it means f double prime of x at the x coordinate, since f double prime of 0, which is 6/6, therefore, is greater than 0, then it means that the turning point, which is 0, 0, is a minimum. So we say if f double prime of x at the x coordinate of the turning point is greater than 0, it is a minimum. If it is less than 0, it is a maximum. And if it is 0, it is a point of inflection, which is rare applied. So since our f double prime of x is greater than 0, it is a 6/6, therefore it is greater than 0, then the turning point 0, 0 is a minimum. After getting the nature of the turning point, this is method 1. You can also employ method 2. In method 2, we say you must have the turning point, which is 0, 0, and the first derivative f prime of x, which is 6/6, therefore x. So if that is that, you can have the sign. You can have the sign of f prime of x, then the slope. We can have the x coordinate of the turning point, its left, its right, all of values to the left must be less than the x coordinate of the turning point, and all the values to the right should be greater than the x coordinate of the turning point. You pick a value and substitute it there. Pick a value less than 0, for example, you can pick a -1. When you put it there, we are interested in the sign. You can pick any, but you say you pick a value which is closer, the x coordinate of the turning point. So if you pick a value after 0, which is on its right, for example, you can pick a 1, the answer is going to be a positive. If you pick a 0 and substitute there, then the answer will be a 0. So the negative slope moves like this. When it is 0, it is constant, and when it is positive, it will move like that. And once it forms a U-shaped curve, then it means that the turning point, which is a 0, 0, is a minimum. So if the second derivative is very complex to think about, you can adopt this one and still get there. So finally, our sketch is going to be, this is now the graph of small f of x. We say we expect all the x coordinates. Our minimum x coordinate is 0 and the maximum is a 4. Our f of x minimum is a 0 and the maximum is a 3/4. So on our graph of f of x, we are going to say that if this is x, this is the small f of x, and this is 0, because the maximum is a 4 along the x-axis. 4, we eliminate this other part, because the curve is not defined for all other x coordinates in this other region. Then you eliminate this other part, and you remain with only the part that starts from 0, 0 up to 4 and 3 over 4. But the reason why we draw it there is to ensure that as we are drawing here, we are forming a U-shaped what? Curve. Otherwise, sometimes when you begin from here, you may draw something which is slightly straight, and when you attempt to draw a curve, it may come out properly. So that was the essence of us drawing the U-shape. Then we eliminate this part where the curve, or where the function was not defined, so that it strictly remains within the limits of the endpoints. That is 0, 0 and 4, 3 over 4. So after that, you draw this dotted line to indicate that it is beginning from here and ending there. And if you have used a sharp pencil, there is no harm in shading that part like that, to show that your graph is covering that region. And then you label this part as f of x is equal to 3 over 64 x squared. So that one will now be a graph of our PDF, small f of x, which was non-linear.